one more thing that I think is important to cover when it comes to moment of inertia. We're not going to try to calculate moments of inertia from scratch, but we are going to be able to modify moments of inertia to suit the situation that we are working with. So one thing I mentioned that affects moment of inertia is where is the axis of rotation located. Okay, so that is going to be dealt with using this idea of parallel axis theorem, it's called. So when you have a situation where you know the moment of inertia for a given size and shape and mass and object, but you'll notice when we talked about looking up moments of inertia in that table, all the entries in that table made the assumption that the axis of rotation is passing through the center of the object. So what if the axis of rotation is not passing through the center of the object? How do you handle that? That's what we're answering here. So just to take like a really simple example, this one I originally gave, where you rotate the pen like this, and then you rotate it like this, and you can feel that the moment of inertia changed. Let's see if we can figure out how much it changed. So the way that you do parallel axis theorem is, first of all, you look up the moment of inertia about the center of mass axis in the table. And that we are going to call as ICM. Okay, ICM. I, by the way, is the symbol we use for moment of inertia, I for inertia, and CM for center of mass, to remind us that this is not actually necessarily the moment of inertia of the object. It's only the moment of inertia if the axis passes through the center. So if you have that one, now you want to move the axis of rotation to a different spot. Okay. Now you want to move the axis of rotation a distance d away from the center of mass. Okay, so in my case here, we rotate the pen about its center of mass, and then we move the axis from here to here. So we move the axis this distance. That would be your distance d that I'm talking about here. The new moment of inertia, the new moment of inertia would be equal to the original moment of inertia that you looked up plus the object's mass times d squared. And again, remember, d is the distance that you moved the moment of inertia. Okay, sometimes I call this IP for parallel, because as the name suggests, this only works for if you move the axis of rotation just back and forth. You can't rotate the axis of rotation, but I mean, that's not something you would normally need to worry about anyways. Okay, so let's see this in action. Let's try to solve the problem of the rotating pen that I've been doing. So let's say we have this pen, and the pen we're just going to imagine is a uniform rod whose center of mass is in the middle. So the center of mass, let's say, is in the middle, and the length of the pen is L, and the mass of the pen is M. Okay. If you go back to the table of moments of inertia that you have, and you say, what's the center of mass moment of inertia for a rod of length L and mass M, you'll find that it is 1/12 times ml squared. Now, we would like to move the axis of rotation to a new location. Over here, we want to move the axis of rotation to the end. In so doing, we moved it a distance d from the center, and you'll notice in our case here, we moved it a distance of 1/2 L away from the center. So we're going to have to add a term here, md square. D is 1/2 L, so that's going to be m times 1/2 L whole thing square. So that'll be 1/4 ml square. And so the final total moment of inertia is going to be the center of mass moment of inertia, 1/12 ml square plus 1/4 ml square. And one thing you can actually see in this case is 1/4 is larger than 1/12, right? So actually, most of the moment of inertia in this case is coming from moving the axis of rotation. Only a small amount of it is actually coming from the original rotation. And so, well, let's just keep going here. You can add these two together. You've got 1/12 plus 1/4. You need a common denominator for that. So this is, we can do 1/12 ml square plus, we want a common denominator of 12. So that'll be 3/12 ml square. So that's going to be 4/12 ml square. And 4/12 is 1/3. So it ends up being 1/3 ml square. Now, one thing you can see here is we actually increase the moment of inertia from 1/12 ml square to 4/12 ml square. So we actually quadrupled the inertia of the object by moving the axis of rotation in this case. So, you know, sometimes this is actually, you might think that this is like, you know, why am I being so pedantic about, you know, adding on these little corrections? But actually, a lot of times these corrections are even more important than the center of mass moment of inertia. So in this case, 3/4 of the moment of inertia is coming from where the axis is located, and only 1/4 of it is actually coming from the main properties of the object. And so if you do this experiment again, like this, and then redo it like this, and you think about, does it feel 4 times heavier than it did? And that's actually seems pretty plausible. It makes a big difference going from here to here. And so that's how you handle, you'll use this idea whenever you need to do a rotation where the axis of rotation is not in the center of the object. Then you immediately think, okay, I'm going to need to use parallel axis theorem on this to move the axis of rotation from the center.